Hello, my name is Matthew Rains. I worked with Kyle Niven, and we are here's the video for the final project for Propulsion. So we're going to start creating a new fluid flow fluent, and then change geometry to 2D, and then we're going to import geometry, and then edit and design modeler. This geometry was based on the theory portion of the project. The turn angles were calculated to be around 10.7 degrees for the first and 11.8 degrees for the second. So once we're in here, we just click generate. Everything should show up, and then we can close. Now we're going to go into meshing. Okay, so meshing is loaded. We're going to right click meshing and then insert sizing, and then we're going to select that face here. And then for this video, we'll do 0.005 for our element size. And then we're going to click generate and then just wait for that to finish. Alright, so our mesh is finished. We can look at it here. It's very nice. We stuck with the default quadrilateral method because that seems to give the best results for the simulation. So now we're going to go to Edge and then create our name selections. So right click and then go to Create Name Selections, or you can use the hotkey. So we'll name this our inlet. These two sides will be our walls, and then this will be our outlet, and then this will be our diffuser. Well, it's the supersonic inlet, but we'll call it diffuser just so it doesn't get confused with inlet. So this square is like our control volume, or rectangle, sorry, is our control volume. This is the inlet, these are the outlets, and then this is the diffuser itself. And then these are just the boundaries of the control volume. So now we have all those, we can close meshing. And then right click, and then click update. So now let's load into setup. Make sure we're 2D. And then we're going to do double position with 5 process solvers, or solver processes. Alright, so the mesh is done. Or sorry, it's finished loading the mesh. So we're going to click density based solver since it's compressible. Turn energy on in our models. And then make sure that viscous is on K omega. And then we're going to go to materials, air, change it to ideal gas. And then boundary conditions here. Make sure everything is a wall except for our inlet and outlet. So outlet will be pressure. The inlet will be pressure far field. And we're going to change the Mach number to the calculated value, 2.1183, about. So that's now our inlet conditions. We can initialize. And then we can run the calculation. We'll do like 250 iterations. That should be enough time. And then we'll calculate, and then we'll come back when this is finished. Alright, so now the calculation has finished. So we're going to make our contours and plots. So right click contours, click new. We'll start with the pressure one. I'm going to select everything here, save display. So as we can see, we have our low pressure initially because of the high Mach number. We hit our first oblique shock, we have a pressure jump. Second oblique shock, we have another pressure jump. And then we have our third shock where we have a large increase in the pressure. Now it is slightly subcritical, right? The normal shock is not quite at the inlet, it's a little bit in front of it, but it is fairly close. So it's just a little bit subcritical, but not horrible. Then we'll do Mach. Go into velocity and then Mach number. Same thing, select everything. Right, same trend, but just reversed. High Mach number. Our Mach number will decrease. It should be around 1.72 or 1.73 according to the math, and it looks correct based on the legend here. And then it should be 1.3 after the second, which again looks correct right in that yellow here, just below 1.35. And then after the shock goes subsonic around this range here. All right, close to that. Calculated value was 0.786. So you repeat that for all the contours. So we'll do velocity, and that's just velocity magnitude. Go, same trend as Mach number. We have pressure one is already done. We'll do temperature. That's here. Again, same trend as pressure. And we have total temperature. And then we're going to go here, and then instead static, we'll do total, with same as stagnation as well. So we see the total temperature stays fairly constant through the oblique shocks, and then it does have a bit of an increase after the last shock. All right, so shocks are expected to be adiabatic, so it shouldn't change much between shocks, but we do have an increase throughout this range. Now there is viscosity, so of course it's not isentropic flow. There is going to be losses and friction, so it will change slightly, even though the math says it will be constant just because of those losses. And then pressure, same thing, go to pressure, and then total pressure, and we can save display. And we can notice we have a increase after the first. It's not as noticeable, but there is definitely a difference. Increase after the second, and then a large change after that oblique, or sorry, that normal shock. And then same as before, right, we do have a change throughout because of that friction and other things. Now we're going to make our plots. So we're going to go to here, XY plot, click new, and then we're going to have to create a new surface line. And this is going to be based on the geometry. So for our geometry, the line through the inlet is at y 0.1. And then our x will be 0 to, we'll do like 1.6. It should only display what is needed. And then we'll just call this the sensor line, and then close. So we'll start with pressure because we have that here. So just click center line, save plot. And as we can see, it follows the trend what we'd expect. We have our pressure starting at gauge pressure, right? This is gauge, not absolute. So it's 0, and then it jumps after that first oblique shock. And then after the second oblique shock, it's a little bit stronger, bigger jump. And then after the normal shock, a very large jump, and then slowly starts to increase as the flow decelerates. If we create a new plot here, we can do Mach number plot. We're going to go to velocity, Mach number, and then same thing over the center line. Once again, the same trend as expected. We have our initial Mach number around 2.12, and then our shock happens, it drops, stays fairly constant, second oblique shock, drops again, and then the normal shock, big drop, and it goes subsonic. So still supersonic here, and then goes subsonic after, and then continues to slowly level out. And then it's the same process for the others. Velocity plot, we can do velocity, magnitude across the center line, same trend as Mach number. We have temperature, should be the reverse or the same general idea as pressure. And then we can do total temperature. And again, we can see fairly constant, little bit of change, and then we do have that increase after the shocks, after that bow shock, and then we have the total pressure. Pressure and total. Same thing across the center line. And this one, right, drops after the shocks, and then it starts to increase throughout the nozzle. So not perfect, but with the losses and friction and other things, right, it's not quite what we expect from an ideal case. So that is the project for propulsion. Thank you for watching.